Hello, I'm Maxim Bernard from University of Potsdam, Germany. Welcome to this introduction video to PecubeGUI, a new graphical user interface for Pecube that I designed. In this video, I would like to give broad introductions of the interface, the beta version, and to show you the main functionalities. The interface has been designed to help the community to use Pecube, but also include additional functionalities and diffusion model, for example, for low temperature thermochronometers like helium on apatites. So yeah, let's start. So here you see the main interface when you open PecubeGUI. And in this video I will use a preset project to show you the main functionalities. So you can create your own project, but you can also create new project here in this button. And I will go through this area here where you can plot your model outcomes. So I will load my preset project here. So when you open a project and this is the main interface, how it looks like. It's designed like Pecube to provide your input parameters. I divided the interface in 8 main tabs called topography, time evolution, thermal parameters, data, tectonic, isostasy, inversion, and output. I will go through all of them. So let's start now with this topography tab where you can actually, this is where you load your input topography to load into Pecube. And you have several functionalities. One of them is you can directly download a topography from this interactive map, which I did here. I will use the Rhone Valley example. Just have to click and drag, and the DM will download, and you can then load any TIFF files into the interface to have your topography. You can also build a sinusoidal topography here, a simple topography to explore a bit the effect of topography on the thermal field evolution. So I already downloaded and uploaded into the interface this topography of the Rhone Valley. I can show you here. It might happen you have like visualization issue, so you have this factor called relief factor here to help handling this scaling factor for relief. This is not actually an input parameter, but it's just for visualization purposes. So overall, this interface is like on the left part here, you will have the main input parameters, and then on the right part here, you will have like visualization and extra parameter. We will go through this. So you can recognize maybe here the resolution of your model you can set here, the latitude, which is already set here, but you can set like the resolution here and the N-skip parameter to actually we can visualize here. This is the Rhone Valley, right? And with this N-skip parameter, if I put it to 1, for example, I click and update, you can see here the resolution increase, right? So I go back to 10. So then you can go and do this time evolution parameter. This is the tab. This is where you can set the time evolution of your input topography, and you already seen an example here. So what you can set is the reference elevation from which you want to apply this amplification and offset parameters, and this is what I did here, and that's why some issues. So what I did here, for example, topographic scenario, like we start with a plateau 15 million years ago with an amplification of 0. And then as we go through this history, we can visualize the topography evolution here. And then from 1.5 million years ago, we have incision of the topography due to, for example, glacial incision. So this is a way you can visualize your input topography before running a Pecube model. Then you have the thermal parameters. So this is where you set the thermal parameters for Pecube, basal temperature, thickness of the crust, etc. And then you can visualize the 1D geotherm actually, and you have the extra parameters here that are used, can be used to compute the heat production rate here. And for example, if I change this value to 2.1, I have the effect on the geotherm. Can visualize is to have a first sense of how these thermal parameters can influence the thermal field. So for example, we can play with this mean erosion rate to see how it impacts the geotherm, and you can see here that due to advections of the heat, the geotherm increase, right? All right. You have additional parameter here, use e-folding depth, and this is to decrease exponentially the heat production rate according to the depth. We won't use it now. Then you have this part where the data part, where we have seen this example, we have data from the Rhone Valley, and we want to upload them in the interface and predict ages at this specific location. So you can copy here, you have a table, you can copy and paste from an Excel worksheet the sample and coordinates and elevation. And then you have, after like all the thermochronometers, and this is where you put the number of observation per sample you have for each thermochronometers. Once you've done that, you can click on show update age, and we have this tab that open, and then this is basically where you can set all your kinetic parameters for each thermochronometer. So we have here example on iridium, thorium, helium ages and fission track appetite ages, and we can set, as I said, like PecubeGUI includes radiation damage model for helium thermochronometry, so you can set one of these models, stopic distances, and in this table below you have the sample ID, and you can provide your observations, observed ages for each grains, radius, and uranium thorium content, and R0 kinetic parameter for annealing of radiation damage. We can do the same for fission track. Right now it's a bit simple, observed ages, observations, and you can set the annealing model you want. So then an additional functionality to help the user to check for their input parameters is to check the sample location, right? We provide samples and we want to make sure before running a model that this is the location we expect. So this is a way to check the sample location. Another good way to check your input parameters is to check the sample elevation. As we decrease the resolution of the DDM to decrease the computation time of the model, we might have discrepancies between our observed elevations and what is predicted in Pecube. So here you can evaluate how far your sample location are from the predicted, and it can influence the edge prediction, so then it will be useful when you want to interpret your predicted data. So for example here there is one sample that is a bit off of the observed elevation, so we'll be and have to take care of this. Then we move to the tectonic tab. This is actually where you can set and yeah, your tectonic scenario. So either no uplift, block uplift scenario, you recognize some parameters. It's the four corners of the model. You can set the factor of amplification for the tectonic uplift. And then you have faulting here. And this is where you can actually provide the fault parameter. I can give you an example here. Here we want, if we want a fault, we can define with 3 points. We have the preset coordinate of the faults plan. And then if we put 3 points here, the table below updates. And then we can provide the distance of each geometry point from the fault line on the surface. So let's say 60 depth is negative here, and then from 10 kilometers we want plan, and then let's say at the fault location or at this elevation, and we can check actually whether this makes sense in this model. So if we click to show faults, we have this tab that appears, and we can visualize our topography with the fault. Looks great. Okay, and we can define our kinematic here with this table that updates according to the number of steps you want. Let's say we have from 15 to 0 constant velocity, slip rate along the fault. Let's say minus for 0.5. Minus is for the thrust faults. And we can check here compute velocity. So we can visualize here. You see the scaling velocity field, and you can, according to laptop capacities, you can decrease the field density up here and the scale to improve the visualization. But this is a way to check again before running a Pecube model what it looks like before. So we can go back here, whatever. And then you have these parameters: isostasy, a lithosphere characteristic of the lithosphere to compute isostasy, the grid resolutions, as it was in Pecube version. Then you have this inversion tab where you can set the number of cores you want for your inversion to use, and then all these parameters that set how the inversions will work. You have additional function for the inversion mode. You can set the misfit function you want, the chi-square corrected. It's basically from the equation 9 in Jean Braun's paper 2012, and you can set the L1 norm if you prefer. Then novelty maybe to give more control on the weight of the age of each thermochronometers for the misfit calculation. You can set each weight. It allows us to have more control on the misfit calculation. And then you have this output tab that allows you to, for example, save the time temperature path to predict edges, and then here the echo input file if you want to show the parameters value. So if you want, and then when everything is ready, you can run a Pecube model, and then you have here a console that shows you all your input parameters that you can double check. Alright, so when your model is finished, the console tells you, and then we can investigate and explore a bit the model outcomes. Just before this, I would like to mention that then when you finish to run Pecube, this button is enabled now, and then compute ages mean actually you can, if you wish, change the kinetic parameters for example, the radius here, and just you don't have to run Pecube again and just compute the, the, the edges, as it's actually called an external program that computes thermochronological edges. And as we have actually the thermal path from Pecube, we don't have to rerun Pecube. So this is a way to explore and not rerunning Pecube when you have large models. Anyway, let's move to the plot part. And then if we want to plot our model result, we load the project, we search for the input file here, and then the interface will search for all the plots we can actually plot. So here you have a list, and this is all what we can show in the interface. So the first one, of course, is the edge comparison, the observations versus the predicted edges for all the thermochronometers. So obviously here it's not the best model though, but it's for the example. And then you can, for example, have the DTU plot and an edge transect. For example, we can choose from latitude along longitude or projected. You just have to draw a line and you click OK, and then you can have here the edge versus distance. You can remove the data from the plots. You can show the thermal path for each here samples. We can also the edge elevations for all thermochronometers, and of course some additional function we can map, for example, the temperatures. It's actually to make 2D maps. So for this we'll go and search for this Pecube VTK file, and then we can choose the temperatures here. If we want a contour plot of elevation, let's say number of contours 10, we click on temperature, and actually what I would like to show you, we can plot, for example, let's say the temperature at depth. So for example, at depth 1 kilometers, what's the distribution of our temperatures at the end of the model run. So here you have an example of the distribution of temperature at 1 kilometer depth, and we see, for example, that below the summit, at 1 kilometer below, the temperature is much colder than in the valley, and this is due to the heat advection and also the topographic effect at this depth. Alright, you can visualize 3D models as well. If you go here, and we have, for example, these Pecube files, that is actually where we have our distribution of temperature. And if you have data, you can show the data location on these 3D models. So that's it for this broad introduction of PecubeGUI. I hope this video has been useful. And I would like to mention you can have more details and in the online documentation of PecubeGUI here in the readthedoc.io website, and extended usage, and you can have much more details on what you can do within the interface. So we'll go further in more details in other and following videos, but since then, goodbye.